Okay, in this video we're going to go through a curve sketching algorithm. We're going to sketch a curve, but this curve we're going to graph an exponential function, or a function with an exponential in it. So here's the function that we're going to graph, e to the power of negative x squared. So the algorithm, or the steps are the same as when we graphed other types of function. So the first thing we look at is x-intercepts. Those you get by setting f at x equal to 0. Now for this one, f at x is never 0, right? That would be 0 equals e to the power of negative x squared, but an exponential term is not true for any values of x, so never true. Therefore, no x-intercepts for this function. Y-intercept would be next. That one you get by letting x equal 0, so f at 0. So that'd be e to the power of negative 0 squared. So e to the power of 0 is of course 1. So therefore the y-intercept is 1, or the coordinates would be 0, 1. The next thing we would look for would be asymptotes. There's no vertical asymptote because it's not a fraction. There's no denominator, so there's no vertical asymptote. For a horizontal asymptote, remember you're looking for end behavior. What happens as x goes to negative infinity or infinity. So as x goes to plus or minus infinity, it's going to be the same. Think about what's happening to f at x. F at x, remember, is, let's make sure we write it down here. F at x is e to the negative x squared. So as x gets very large, becomes a very positive number, this exponent here, x squared, is going to become very large, but there's a negative, so it's going to be a very large negative number. So the exponent is going to be approaching negative infinity. So e to the power of something approaching negative infinity, that approaches 0. So f at x is approaching 0. And if as x approaches negative infinity, it would be the same thing because it's x squared, so you would still be approaching infinity, and then negative infinity because of the negative exponent, and e would be to the power of something very large negative values. So the end behavior is f at x is approaching 0, meaning there's a horizontal asymptote of 0. The next step is to look for intervals of increase and decrease. So to do that, you have to find the first derivative. So the first derivative of this function is e to the power of negative x squared times negative 2x. We set this equal to 0. E to the negative x squared will never be 0, but negative 2x will be. So you're going to look at when does negative 2x equals 0, which means x equals 0 is the critical number. So now to figure out if it's increasing or decreasing, we'll set up an interval table. So from minus infinity to 0, and 0 to infinity, and we're going to look at the sign of f prime. So take a negative number, or a number between minus infinity and 0, sub it into this equation, and this will be positive. And if you take a positive number, you would get a negative. So it goes from increasing to decreasing. So therefore, f at x is increasing if x is less than 0, and f at x is decreasing if x is bigger than 0. The next one would be maximum or minimum values, and by the first derivative test there is a maximum value at x equals 0. And we already know the y value when x equals 0. That was the y-intercept. So that would be the point. Zero, 1. Okay. Now, after that, we look at concavity. So we have to take the second derivative. The second derivative of this function, what was the first derivative? So the first derivative, just write it down here, was negative 2x e to the minus x squared. So we'll have to use the product rule. We'll take the derivative of the first term, be negative 2 times the second term plus the first part times the derivative of the second, which would be that. You simplify that, you get, well, we've got a common factor of negative 2 e to the minus x squared. Then we're going to have 1 minus 2x squared. Okay. To find the concavity, we'll set that equal to 0. So this part will never be 0, but this part will be. So 0 equals 1 minus 2x squared. Solving for x, you're going to get plus or minus the square root of 1/2. Set up an interval table. So we're going to go from minus infinity to minus square root 1 over 2, minus square root 1 over 2 to square root of 1 over 2, square root of 1 over 2 to infinity. And we'll just test the first derivative here. You can look at all the factors if you want, but if you took a number less than negative 1 over 2, so something like negative whatever, 10, subbed it into the second derivative, you get a positive number between minus infinity and, minus 1 over root 2 and root 1 over 2. You, like 0, sub in 0, you would get a negative number, and in this interval you get a positive number. So it's concave up, concave down, concave up. So we can state that, therefore f at x is concave up if x is between minus infinity and negative root 1 over 2 and root 1 over 2 to infinity. and f at x is concave down if x is in this interval. Okay. There will be 2 points of inflection, one at negative square root of 1 over 2 and one at positive square root 1 over root 2. To get the y values, you would have to substitute those values in. So we need f at minus square root 1 over 2. And it turns out that's the same as f at square root 1 over root 2. In both cases, you're going to get 1 over the square root of e. So the points of inflection are negative 1 over 2, 1 over root e, and square root 1 over 2, 1 over root e. Okay, so now it comes down to graphing this function. So draw your axes, set up your scale so you can plot all your key points. Remember our maximum y value was 1, so which happened at 0. We had a couple key x values, 1 over root 2 being 1, and negative 1 over root 2 being the other. These two points of inflection, the y value 1 over root e, so remember root e is 2.78, so the square root of 2.78 is a little less than 2, so you're going to get a point around here, y value be somewhere around here. Same thing on this side. The function was increasing. Remember there was a horizontal asymptote, so it approaches the x-axis. Horizontal asymptote was 0. The function is increasing to 0 and then decreasing. It's concave down between these two values, and then it switches to concave up but approaches the asymptote. Maybe a little smoother than I drew it. And the same thing over here. Okay, so concave up, concave down, concave up, and approaching the y-axis. So something like that. Maybe a little bit more of a curve when you draw that, but something like that.